Prime numbers. In some sense, the most important positive integers are the prime numbers. Prime numbers are the building blocks of all other positive integers. Before we can discuss how powerful prime numbers are, we need to discuss simply what they are. What exactly is a prime number? Recall, first of all, that 1 is a factor of every single positive integer. Recall also that every positive integer is a factor of itself. 3 is a factor of 3, 7 is a factor of 7. Thus, every positive integer has at least these two factors. Now, of course, many integers have many more factors, and in fact, in a previous video, we talked about counting the number of factors for large numbers. A prime number has only these two factors, 1 and itself, and absolutely no other factors. In other words, a prime number is not divisible by any number lower than itself other than 1. So that's the fundamental definition of a prime number. Here are the prime numbers less than 20. You definitely need to know that those 8 numbers are prime. You definitely need to recognize them instantly as prime numbers. That's very important. And in fact, I'll say, here are the ones between 20 and 60. It would be a very good idea to know each one of these is prime as well. You don't want to get stuck on the test having to figure out, now wait a second, is 51 a prime number? Is 53 a prime number? You don't want to have to do those calculations in the middle of the test. It's better just to know that these are the prime numbers. Above 60, you rarely need to know whether those numbers are prime. It's easy enough to figure out in the few instances where you would need to know that. If you're gung-ho about memorizing primes, memorize them all the way up to 100, but you don't need to do so. Here's some important prime facts. Notice, first of all, 1 is not a prime number. Prime numbers have two factors, 1 and the number itself, but 1 only has one factor, itself. Now, I know some people get almost sentimental about this, and they feel like 1 is being cheated, or somehow it's being artificially excluded from the elite club of prime numbers. So I just want to assure you, yes, mathematicians could have bent the rules. They could have made 1 a prime number if they wanted. There are actually very sound mathematical reasons why mathematicians have chosen to define it this way, so that 1 is not a prime number. And in fact, if you're interested in some of these reasons, I highly suggest underneath this video there'll be a link to a GMAT blog about this very topic, and I'll go into that in a little more detail in that blog. But the important fact to recognize here, 1 is definitely not a prime number. Notice also, 2 is the only even prime number. All other even numbers are divisible by 2 and hence are not prime. So every prime number in the world is odd except for 2. 2 is both the lowest prime number and the only even prime number. The test absolutely loves to test these two facts. I would say more than 50% of the time when they're asking questions about prime numbers, at least one of these two facts is hidden somewhere in the question. They're extremely important. Now, we can talk a little about testing whether a larger number is prime. To test whether any number less than 100 is prime, all we have to do is check whether it is divisible by one of the prime numbers less than 10. If a number less than 100 is not divisible by any prime divisor less than 10, then the number has to be prime. And of course, the only prime divisors less than 10 are 2, 3, 5, and 7. So those are the only divisors we have to check. And if it's not divisible by any of those numbers, it is a prime number. So for example, here's a practice problem. I'm going to say pause the video and work on this problem now. Okay, for all the positive integers n, such that n is somewhere between 80 and 90, how many prime numbers are there? Well, fact number 1, we know obviously none of the even numbers can be prime because they're all divisible by 2. So we're only looking at the odd numbers. So here are the odd numbers in that sequence. Obviously 85 ends in a 5. It's divisible by 5, so we can eliminate that. Well, now you may know that 81 is 9 squared. So it's divisible by 3, it's divisible by 9, so that's obviously not a prime number. If we use our divisibility tricks, we can check for divisibility by 3. 8 plus 3 is 11, not divisible by 3. 8 plus 7, 15, that is divisible by 3. 8 plus 9, 17, not divisible by 3. So 87, the digits are divisible by 3 when we add up the sum of the digits. So that means that 87 is also divisible by 3. Another way to see that, incidentally, obviously 90 is a multiple of 3. 90 minus 3 is 87. So that means that 87 has to be a multiple of 3. So we can eliminate 87. That leaves us with 83 and 89. So we've already checked 2, 5, and 3. That leaves us with 7. Well, think about this. 7 obviously goes into 77. Add 7, it goes into 84. Add 7, it goes into 91. Those are the multiples of 7 through this region. And the multiples of 7 pass through the 80s. They land on the even number, 84. They don't hit any of the odd numbers in the 80s. So 83 and 89 are not divisible by 7, and therefore they are prime. So those are the two prime numbers in that region. In summary, we discussed the definition of prime numbers and listed the first few. We talked about the very important point, 1 is not a prime number. We talked about the other important point, 2 is the only even prime number, the lowest prime number and the only even prime number. And we discussed a procedure for testing whether a number is prime. Prime factorizations. This is a hugely important topic. First of all, here are the first 17 prime numbers, all the primes from 2 up to just below 60. And of course, the first 8, those are non-negotiable. You absolutely need to know those, and the others are very good ones to know as well. In the last video, I suggested that prime numbers were the building blocks of all the positive integers. Now we can discuss what this means. And in order to talk about this, I'm going to introduce the name of an important mathematical theorem, the fundamental theorem of arithmetic. I'll say right now, you don't need to know this particular theorem. As it was first discussed by Mr. Euclid. You don't need to know that, but you do need to know the idea of this theorem. Every positive integer greater than 1 must either A, be a prime number, or B, be expressed as a unique product of prime numbers. So in other words, every integer greater than 1 that's not prime can be expressed as a product of primes. And this product is called the prime factorization of the number. So that core idea you definitely need to know. Let's talk about this prime factorization. Let's do some examples. So first of all, 9 is obviously 3 times 3. It's a product of 2 prime numbers. 10 is 2 times 5. That's a product of 2 prime numbers. 12, we could write that as 4 times 3, but 4 isn't a prime number. 4 itself we can write as 2 times 2. So we can write 12 as 2 times 2 times 3. That's a product of prime numbers. 15 is 3 times 5. 24, we could write that as 8 times 3. Well, 8 is not a prime number. We can write the 8 as 2 times 4. 4 is not a prime number. We can write that as 2 times 2. If we had realized that 8 is 2 cubed, we could have skipped directly ahead to say that 8 is 2 times 2 times 2. Well, 2 times 2 times 2 times 3 is the prime factorization of 24. And in fact, we can even write this way with an exponent, 2 to the third times 3. Either way is correct to write it. When the numbers tend to get larger and you have lots and lots of prime factors, it's usually more convenient to write it in exponent form simply because it's more compact. So here are some larger numbers. Now 100, you might be able to see 100 is 10 times 10. Each 10 is 2 times 5. So that's how we get 2 squared times 5 squared. Here are some other ones that are a bit larger. You don't necessarily need to worry right now about how we found these. These are just to show you some examples of prime factorizations. Let's talk about how to find the prime factorization of a slightly larger number. So for example, suppose we're looking at the number 96. What is the prime factorization of 96? You might want to pause the video and work on this right now, and then I'll discuss it. So the prime factorization of 96, well, certainly it's divisible by 2, so we can express it as 2 times 48. 48 is 6 times 8. Well, from there, 6 is 2 times 3. That's the prime factorization. 8 is 2 times 2 times 2. then group everything together. We have 1, 2, 3, 4, 5 factors of 2, so we can write that as 2 to the 5th times 3. That's the prime factorization of 96. Notice that 96 would be divisible by 2, 4, 8, and 16. Those are powers of 2. And by 6, 12, 24, and 48. Those are those 4 powers of 2 multiplied by 3. All of those would have to be factors of 96. Notice it would not be divisible by 15 or 18. It's not divisible by 15 because 15 involves a factor of 5, and there's obviously no factor of 5 in 96. 18 is a little trickier. 18 is 2 times 3 times 3. You need 2 factors of 3. 96 only has 1 factor of 3, and therefore 96 cannot possibly be divisible by 18. So here I've just shown an example of a very important idea. One way to say it is the following. The prime factorization of a number is like the DNA of the number, revealing all its essential ingredients. Any factor of Q must be composed only of prime factors found in Q. So that's a tricky idea. We're going to talk about this for a few minutes because it's a tricky idea. First thing I'll say is, remember our synonymous statements from some earlier videos. We have these 4 statements. R is a factor of Q, R is a divisor of Q, Q is divisible by R, Q is a multiple of R. All 4 of those mean the same thing. Well, we can add a 5th statement now. Every prime factor of R is included in the prime factorization of Q. That is equivalent to the other 4 statements. Let's talk about an example with actual numbers. Suppose we are told that 4,680 has this prime factorization. Someone just hands us the prime factorization, which is awfully nice. Given this prime factorization, we want to know which of the following numbers are or aren't factors of this number. So I'm going to say pause the video and see if we can use the prime factorization to figure out whether each number here is a factor of that number. So for 25 obviously is 5 times 5. We need 2 factors of 5. We have only 1 factor of 5, so that's not going to work. 25 does not work. 45, well, that's 5 times 9, or 5 times 3 times 3. Well, we have a factor of 5 and we have 2 factors of 3, so that works. 65 is 5 times 13. Well, we have a 5, we have a 13, so that works. 85 is 5 times 17. We do not have a factor of 17, so that's not going to work. 120, well, that is 40 times 3. 40 is 8 times 5, so we have a 3 and a 5 and then an 8, which is 2 times 2 times 2. Well, we have a 2 cubed, we have a 3, and we have a 5, so that we're all set. Means that this would be divisible by 120. 180, well, that is 30 times 6. 6 is 2 times 3. 30 is 6 times 5, so we get 2 times 3 times 5, so we need 2 powers of 3, 2 powers of 2, and 1 power of 5, and we have all that in the prime factorization of 4680. So in other words, 4680 would be divisible by 180. That would actually work. So we've used the prime factorization to figure out whether these other numbers could be divisors of 4680. That's just one example of how prime factorizations can be useful. In the upcoming videos, we'll be showing many different examples of how we can use prime factorizations to answer a number of different integer property questions. Finding the prime factorization of a number is definitely the single most important skill in the entire integer property section. It's critically important to practice this skill until you are extremely comfortable with it. In summary, we talked about what the prime factorization is and how to find it, and we talked about how the idea of prime factorization connects with the ideas of factors and multiples. Counting factors of large numbers. Consider this question. How many factors does 8400 have? Well, that's a large number. For smaller numbers, numbers less than 100, we could simply list the factor pairs, but that would take too long for a number as large as this. Fortunately, there's a trick we can use to answer this question. So this trick involves a 4-step procedure. Step 1 is simply finding the prime factorization of the number. Okay, that's something we can do. Clearly, 8400 is 84 times 100. 84 is 7 times 12. Of course, 100 is 10 times 10. Break this all into prime factors. Group these all together. We get 2 to the 4th times 3 times 5 squared times 7. That's the prime factorization. We need to get the prime factorization into this form with powers of the prime numbers. So we actually need those exponents. Because step 2 is we're going to make a list of the exponents of the prime factors. Well, this is a bit curious. Clearly, 2 has an exponent of 4, 5 has an exponent of 2, but the 3 and the 7, they're just kind of sitting there. They don't have an exponent, it looks like. Whenever you have one factor of something, that's really an exponent of 1. We don't write the exponent of 1 because it would be redundant, but it really has an exponent of 1. And therefore, reading across, those exponents are 4, 1 on the 3, 2 on the 5, and then 1 on the 7. 4, 1, 2, 1. That's our list of exponents. So that's step 2. We have this list. Step 3, add 1 to every number on the list. So we had 4, 1, 2, 1. Add 1 to each one of those numbers. We get 5, 2, 3, 2. That's our new list. All we've done is we've added 1 to each number. Once we have this new list, multiply all those numbers together. So 5 times 2 times 3 times 2. Well, clearly 5 times 2 is 10, 3 times 2 is 6. Multiply this together, we get 60. The number 8,400 has 60 different factors. So those factors, of course, would include 1, which is a factor of every number, and 8,400, of course, every number is a factor of itself. So those would be 2 numbers on the list. Altogether, there are 60 numbers on this list. At the end of the video, I will discuss why this procedure works. Let's review the steps. To find the number of factors that positive integer n has, find the prime factorization of n and write it in terms of the prime factors, powers of the prime factors, because we actually need those exponents. Step 2 is create a list of the exponents. Remember to use 1 for a prime factor that has no exponent. Once we have that list, step 3 is add 1 to every number on the list, creating a new list. And once we have that new list, multiply them all together. Find the product of that new list. That product is the number of factors n has. Let's practice on another large number. How many factors does 21,600 have? Well, first of all, why don't you pause the video here and try this on your own, and then we'll talk about it. First, the prime factorization. Well, clearly, 21,600, we can write that as 216 times 100. Let's just handle the 216 separately first. The 216 is 2 times 108. And the 108 is also divisible by 2. That's 2 times 54. 54, we can write that as 6 times 9. And then we can break those into individual prime factors and get down to this, the prime factorization of 216. So, incidentally, you could find the prime factorization of 216 if you happen to notice that 216 is 6 cubed. So 6 cubed would be 6 times 6 times 6. That's 2 times 3 times 2 times 3 times 2 times 3. If you notice that, that would be a shortcut. We didn't need that. We actually got to the prime factorization anyway. So now we multiply this by the prime factorization of 100, which of course is 2 times 5 times 2 times 5. Collect everything together. We get 2 to the 5th times 3 to the 3rd times 5 squared. That's the prime factorization. Well, now we're in the home stretch. Now it's easy. Now we simply make a list of those exponents, 5, 3, 2. Those are the three exponents of the prime factors. We add 1 to every number on the list, 6, 4, 3, and we multiply those together. And of course, that 4 times 3 is 12, so we get 6 times 12 is 72. This number, 21,600, has 72 total factors. Again, one of those factors has to be 1. One of those factors has to be 21,600. Those would be two factors on the list, but there are 72 factors on the list altogether. To find the number of odd factors, basically we would repeat this procedure, but ignore the factors of 2. So we'd find the prime factorization as usual. We'd make a list of the exponents of odd prime factors, the odd prime factors only, pretending that powers of 2 did not exist. Once we had that list, we add 1 to each number on the list and multiply the numbers on the new list together. That's the number of odd prime factors. So here again is the prime factorization of 21,600. We're going to ignore that 2 to the 5th. We're going to pretend that doesn't even exist. The only exponents that interest us are the exponent 3 and the exponent 2. Those are the two exponents on the odd prime factors. So our list is just 3 and 2. Add 1 to each of those, we get 4 and 3. Multiply those two, we get 12. There must be 12 odd factors. We have no direct way to calculate the number of even factors. We have to calculate the total number of factors and the number of odd factors and then subtract. For example, 21,600 has 72 total factors, 12 odd factors, so it must have 72 minus 12, 60 even factors. At this point, I will discuss a little about why this procedure works. If you understand this, it will help you remember the procedure, and it will also help you on other kinds of math problems. So it actually is not a waste of time at all to really understand why this procedure works. But knowing this is not strictly necessary for the test, so if you don't want to learn anything beyond the bare minimum you need for the test, you can just skip the rest of the video. That's perfectly fine. So, why does this work? Let's go back to 21,600. That's the prime factorization. The factors of this number must be built of these prime factors. Remember what we discussed in the last video. That's one of the uses of the prime factorization. It allows us to see any possible factor of the number. If factor f is built of these prime factors, how many powers of 2 could f contain? Well, f might contain no factors of 2 at all, or it might contain some. It might contain any number up to 5. Therefore, the possibilities are 0, 1, 2, 3, 4, and 5. That's 6 possibilities. That's a list of the possible number of factors of 2 that f could contain. Similarly, the possibility for factors of 3 are 0, 1, 2, 3, 4 possibilities, and the possibilities for factors of 5 are 0, 1, and 2, 3 possibilities. F could contain no factors of 5, it could contain one factor of 5, or it could contain 2 factors of 5. Those are the possibilities. Any of those possibilities could go with any of the others, so we multiply them. Here's a slightly different way to say the same thing. It's as if we have 3 slots and we get to make whatever choice we want in each of the 3 slots, 3 separate choices. So here what we're doing is we're trying to build a factor of 21,600. In the first slot, we get to pick how many factors of 2 do we want. We could choose anything on the list from 0 to 5. So that's 6 possibilities for that first slot. In the second slot, we want to know how many factors of 3 do we want. We could pick anything from 0 to 3. In the third slot, we want to know how many factors of 5 do we want. We could choose anything from 0 to 2. Now notice, suppose we picked, for example, 0, 0, 0. We picked 0 in all 3 slots. That would produce the factor of 1. And 1, of course, is a factor of 21,600 because anything is 1 is a factor of anything at all. We could also max out the list. We could max it out, so we pick 5 in the first slot, 3 in the second slot, 2 in the third slot, and of course what that would do is give us 21,600 itself. That is the prime factorization of the number. And of course, any number is a factor of itself, so that's perfectly fine. We could get the number itself as one of its factors. Or we could mix and match. We could choose any number in one slot and match it with any number in any of the other slots, and that would give us one of the factors of 21,600. So overall, the exponents of each prime factor of n delineate the possibilities for the individual factors of n. Adding 1 includes the 0 case, because any individual factor of n may or may not include any one of the prime factors. For example, among the prime factors of 21,600, 36 is a factor that doesn't have 5 as a factor. That would mean that we set 0 in the third slot to get a factor of 36. 100 is a factor that doesn't have any 3s as a factor. So we'd have 0 in the second slot to get a factor of 100. 75 is a factor that doesn't have 2 as a factor, so we'd have to have a 0 in the first slot to produce 75. Finally, we multiply the possibilities. 6 in the first slot, then 4 in the second slot, and 3 in the third slot. We multiply those. Why do we multiply them? Well, it may be intuitive to you, the mix and match principle. If this is not intuitive to you, this piece will make more sense when you learn the fundamental counting principle in the counting module. So don't worry about that so much now. You'll get to it later when you study the counting videos. In summary, to find the number of factors of n, here are the steps. You find the prime factorization of n, list the exponents, add 1 to create a new list, and find a product of the new list. There's a similar procedure to find the number of odd factors. If we want the number of even factors, we have to find all the factors, subtract the number of odd factors, and we discussed a little about why the procedure works.